Okay, so I wanted to update you on my uh, coil assembly and explain something. The previous coil that I was running on here, I found out it was only about 3.5 volts, but I overlooked something. The It's pulsing. Because it's pulsing, I wasn't getting my true RMS. Now, by putting on the low 1.6 ohm coil, by putting a 1 microfarad metal film capacitor across the coil, I'm able to get in excess of, well, actually, let's see. If I unplug the load, take the load off, we are now getting 24.4 volts RMS. Oh, yeah, that's a lot better, isn't it? And actually, it's more than that, because if I go and look at the oscilloscope, we have 64 volts peak to peak and a cyclic RMS of 22.8 volts. That's the yellow one. And the blue one, I'm monitoring a different coil. So we're actually doing a lot better with the when we get it back into RMS stage. And there's something else I wanted to show you as well. I'm just going to plug my load back in. So I'm actually sending that power up to my supercapacitors at the moment. It's very interesting what's going on. This flipping wire going. Right. So, okay, the current's not great at the moment, but then the supercapacitors are already charged, because they're actually charging up my battery right now. So at the moment, that I'm getting about 31.7 milliamps out. But what's really interesting is when this thing is loaded down, my actual input current drops right down. So I'm still pulsing with 40. I'm using 41 volts actually at the moment. It's going, and we're actually using 80 milliamps at 40 volts to go through the H bridge. We're pulsing at a few microseconds. I think it's 200 microseconds or something. Well, it shows up on the oscilloscope as 200 microseconds, even though it's more of a RMS cyclic waveform now, because it's smoothed out with the capacitors. Now, what's interesting is the higher I wound two more coils. I didn't count the number of turns actually, because I just filled up the wire. But the higher, the thinner the wire, the higher the voltage on the output on the particular coil is, the lower the capacitance needs to be. And I'm actually got a 10 nanofarad capacitor across this coil. Now this might blow you away, but it's what I'm about to show you. I don't know if you noticed when I went over there, but the other coil on the output, there's 308 volts peak to peak on that coil. There's 308 volts peak to peak, cyclic RMS 100 volt. That's quite a lot of voltage actually. Yeah, so that's on this channel, the blue channel, this probe with the blue band on it. So that's got 100 nanofarad capacitor across it to bring the waveform into cyclic RMS. Now, the other interesting thing, and this is what really kind of got me, is the phase shift. If you look at the two waveforms, you'll notice there's a huge phase shift on those two waveforms. Between the yellow channel is on one side of the transformer, and the blue channel is on the other side of the transformer. So they're both on opposite sides. Now, that is extremely significant, because it's the phase shift which is actually causing us not to see much of a, on the low side. Remember, this is at 16 volt. We're at 16 volts there, right? So that current on the low side is at about 300 milliamps on the low side. right before it's been stepped up to 40 volts, and once it's been stepped up to 40 volts we see 80 milliamps coming out, which is what you expect, because a lot of people make the mistake of assuming that 80 milliamps is very small, but it's not. Well, if you go and do a calculation, I'll show you what I mean, volts to current and everything else. There's a calculator on the internet. You can go and search watts and amps calculator, and you'll get a calculator on the internet. Anyway, let me just go and try and bring this up actually, because it's important that people know about this. Right, I'm just going to go on my keyboard. I'm going to search for watts, amps, calculator, right. Yeah, right, let's just do that. Right, so I'm just going to get this thing up on the internet, because you've got to work out what your watts are really, and I'm not actually calculating any watts right now, but so let's see. I think I've got the right one. Okay, right, let's go to AC single phase. Right, I want to show you this in. Now, what is significant about this, if you go on Rapid Tables, the website, this is a website and you can find it under rapidtables.com, right? So if you, let's say we're pulling out 100 watts, right? Let's say, I'm just going to type this out. Let's say we're taking 100 watts, right? I'm going to type that in the keyboard. And our voltage is, let's see, 15 volts. Let's go with 15 volts AC, and we'll calculate. Oh, I'm missing that out. Enter power factor. Oh, I'm just going to put a power factor of 1 in. Right, power factor of 1. Now, this is what a lot of people don't understand. Right, AC single phase, we are say consuming 100 watts, and the voltage is 15, and a power factor of 1. The current would be 6 point. Look at that, a lot of sixes there. 6.66 amps, right? Okay. Right. So that will be in amps, right? Now, if our voltage was 40 volts, let's change that to 40 volts and you'll see what I mean. Right, I'll go over here. The voltage is going to change to 40. Type 40 and we calculate that. Now this is what you'll find interesting. So 100 watts going in, remember, at 40 volts, and the current in amps is only 2.5, right? 2.5 amps. So it's relative. The bigger the voltage, right? The bigger the voltage for the same amount of watts, and we actually use less current. Now, what happens if I change my watts to my voltage to 10 volts? Let's put 10 volts in. Calculate. Oh, it's actually, look at that. So now with 100 watts, voltage of 10 volts, power factor 1, we are now using 10 amps. right? Same wattage, but we're actually using 10 amps. So this is important when you're doing calculations, when you're working out, because remember, this is 15 volts, right? 15 volts, 16 volts, sorry, going in, stepped up to 40 volts. So the current's always going to be higher at the lower voltage because we're stepping it up. So the current will show up as a higher current on the low side because it has to convert into the watts that we're actually consuming by the device, by the device itself. So it's worth going there because it depends on which way around you're going. I mean, if you're converting up or down, it's all dependent, right? So we're using a static wattage, the watts is what counts, because watts is a constant, really. I mean, if you want to find out, if you know what the wattage is of a bulb, for example, you have to work out how much current that's going to use at various voltages. So, right. Anyway, we're doing pretty well. I mean, now my supercapacitors are charged up now. So what I'm going to do is I'm going to discharge them. I want to discharge the supercapacitor because I'm going to show you what happens when the load increases on this device. So if I can trigger this, there we go, I've triggered it. So it's discharging the power now into my battery, which is over here behind here. So that's charging that up at 1.95 amps at the moment. Right, 1.9, nearly 2 amps going into that. And as that happens, this is discharging right now. The voltage at the top is dropping. So I'm going to wait for that drop to about 4 volts or 3 volts. Oops! Ah! Not my transformer over. My choke. Right, so we'll wait. Now you'll see this. The waveform will start to pulse as the LED flashes. You saw the LED flashing on my device. That's why the yellow waveform is pulsing. Now while it does that, you'll notice that my low side at the moment, the current's actually gone up because we're actually using less current right now because it's discharging. There's no load on it. I'll show you what I mean. We have an output current of 13 milliamps. With an output current of just 13 milliamps, my input current's gone up, which is what I expect with this device. It actually works in reverse. Less load on the device equates to more load on the input, which is the other way around. So the way to fix that is to use a parallel regulator, which basically loads everything down. So that you, instead of a series regulator, you use a parallel crowbar type regulator. Okay, the load just came back. I'm under full load now. And look at my input current, it's dropped. My low side input current has dropped right down to 300 milliamps. And the waveforms are compressed because they're under load. My output current right now is 51.4 milliamps. So my actual output is higher, whereas my input current is lower right now. And the voltage on the RMS has dropped to about 8 volts. On the oscilloscope it shows up as 7.6 volts because we're actually measuring AC. It's climbing obviously because the solar panel's charging up as well. So the solar panel's charging it up, it's supplementary power because it's daylight outside. There's a voltage drop across the LEDs, you see, so the DC will always be slightly lower than the AC. The AC is showing higher because of the voltage drop across the diodes on the bridge rectifiers, which are on here, which I've clicked onto. So that's at 8.6 volts AC, and that's at 8.4 volts AC. So actually no, this is AC as well. Yeah, but there's a slight difference because of the voltage drops across the circuit and everything. Yeah, this is RMS anyway. Anyway, the actual output current is slowly dropping because as the voltage increases, we actually end up with less output current, because that's what you expect. As current always increases, sorry, my hand's shaking a bit. Current output, sorry, the actual load increases when the voltage on the load side is lower. That's what you expect with it. But anyway, so I actually took one of these coils. I took this coil, this top one, out of my choke because it was the same number of turns. And what's interesting is I stuck a 1 microfarad capacitor across that. I'm not actually taking power out of there. The capacitor is just acting as a buffer. So what it does is it smooths out and turns the magnetic gauze that's on this core material down here, turns it into an RMS pulse instead of a spike, so that the bridge rectifier on the other coil can make better use of it. And there's also a capacitor across the other coil as well, which is that one there. So I've got small capacitors, about 1 microfarad across these coils, to tune the circuit, and it actually improves the output even more. So if I disconnect that, oh, actually I can't really do it very easily at the moment because that one's the output is clipped onto the leg of that capacitor, and if I'm disconnect the capacitor, then obviously I'm not going to see anything on the meter. So, but anyway, it's very interesting to see what's going on. Now, input on the 40 volt side is some 70 milliamps on the 40 volt side. Anyway, I wanted to show you that. So I hope you found that interesting. I'll be back later. I've got to go out and do some shopping. I haven't got much money on me, so I'm struggling a bit right now. Tough, but we'll have to get there somehow. Yeah, basically probably set up a pot noodle or something cheap. So go to the rapid tables, do some playing around, you know, experiment with the website I've just been showing you, rapidtables.com, the calculator. Or you can just search for the calculator you want to use. It's very, very useful. You can learn an awful lot. You can punch in some values and see what they come out at. So just to remind you, that's the website. It's a good website. They've got all this stuff: amps to kilowatt, amps to kilowatt amps, VA, variable amps, amps to volts, amps to watts, electricity bill. It's great for calculating your stuff. You can even work out your electricity bill as well. Kilovolt amps, kilovolt amps to watts, blah blah blah. It's all down there. There's absolutely tons of stuff on these websites, these pages. Most people don't even know they exist. I mean, most people don't even know these online calculators exist. So is what I'm saying. And once you know they exist, you can work stuff out. Even if you're not a mathematician, you just use the web page. So anyway, I'm off now. Thanks for watching.